The year is 2010, and on Moon Base Alpha, a shipment of supplies is being prepared for a colony on Titan. The supplies have been loaded into a special pod which sits between a set of rails. A computer closes a switch, and the pod accelerates rapidly along the rail. The force that accelerates the pod was first detected by French physicist André Ampère in 1820. He noticed that when the currents in two parallel conductors were flowing in the same direction, the conductors attracted each other. But when the currents were in opposite directions, the conductors repelled each other. Ampère reasoned that the magnetic fields around the wires created attraction and repulsion forces. The left-hand rule for a conductor predicts the direction of the field around each of the wires. When the fields in between are in the same direction for each of the wires, repulsion occurs. This repulsion is similar to what happens when two bar magnets are placed side by side, so that the field of one magnet is in the same direction as the field of the other magnet. When the electron flow in two wires is in the same direction, then, in the space between the wires, the field produced by one wire runs in the opposite direction to the field produced by the other wire. As a result, the wires are attracted to each other. Again, this is similar to two bar magnets placed such that the fields between them run in opposite directions. These principles explain the mechanism used to launch the supply pod. The launcher, called a rail gun, consists of two rails which can conduct massive amounts of current. The supply pod itself is also a good conductor. When the rail gun is activated, a massive current flows down one rail, crosses through the pod to the other, and returns, completing the circuit. Because of the interacting fields, there is a large force trying to push the rails apart, but they are securely fastened and can't move. The field produced by the current flowing through the pod is in the same direction as the field between the rails. This results in a repulsive force which pushes on the pod. And since the pod is not fixed, the force acting on it is able to propel it down the track at greater and greater speed. The direction of the force on a current-carrying conductor placed in a magnetic field can be easily determined. If the electron flow is in this direction, the field produced around the conductor will interact with the field produced by the magnets. Since the two fields are in the same direction above the conductor is repelled downward. If the direction of electron flow is reversed, then the field around the conductor also reverses. The fields are now in the same direction below the conductor, and so the conductor is repelled upward. This effect is called the motor principle. The motor principle is one of the most important applications of Hans Christian Ørsted's discovery of electromagnetism. But it was British physicist Michael Faraday who in 1821 put all the pieces together and devised the first electromagnetic motor. The motor principle states that if a current-carrying conductor is placed within an external magnetic field, it will experience a force which is perpendicular to both the direction of the electron flow and the external magnetic field. The direction of the force is determined by the left-hand rule for force. Namely, if the thumb points in the direction of electron flow and the fingers point in the direction of the external magnetic field, then an imaginary arrow drawn straight out from the palm indicates the direction of the force exerted on the conductor. Now, if the current is reversed, the thumb points in the direction of electron flow, the fingers point in the direction of the external magnetic field, and the palm indicates the direction of the force exerted on the wire, in this case downward. The motor principle got its name because its first application was in the design of electric motors. A loop of wire carrying a current is placed between magnetic poles. If we apply the left-hand rule for force on this side of the loop, so that the thumb indicates the direction of electron flow and the fingers indicate the direction of the external magnetic field, then the force on the conductor will be upward as indicated by the palm. When the left-hand rule for force is applied to the other side, the palm indicates a downward force. These two forces will cause the loop to rotate about an axis until the loop is vertical. If it rotates past the vertical, these same forces will stop the rotation and return the loop to the vertical position. But to perform work, the loop must continue to rotate. This is easily accomplished by directing the electron flow through a split ring called a commutator, which is in contact with graphite brushes. Initially, electron flow is in the same direction as shown earlier, and the loop rotates as before. But as soon as the loop passes through the vertical plane, the commutator causes the electron flow to reverse. This reverses the direction of the forces on the sides of the loop, which causes the loop to continue rotating. The split ring commutator reverses the electron flow in the loop every half rotation, just at the instant it is required to keep the loop rotating. Normally, we use electric energy to run a motor. But could we use a motor to produce electric energy?